From an egg you could hold in 2 hands to a creature weighing as much as 10 elephants. That is the transformation we're about to explore. The journey of Argentinosaurus, the largest land animal that ever walked the earth. Picture an egg, 15 centimeters across, smaller than a soccer ball, inside an embryo developing in darkness. When it hatches, the creature that emerges weighs about 5 kilograms, 11 pounds, small enough to cradle in your arms. 40 years later, that same animal weighs 70,000 kilograms, 70 metric tons, an increase of 14,000 times its birth weight. It stands as tall as a 4-story building at the shoulder. Its length, from nose to tail, stretches 35 meters. That's longer than 3 school buses placed end to end. Longer than a blue whale. But here's what might surprise you most. This giant shares fundamental biology with the smallest bird you see in your backyard. The same air sac respiratory system that allows a hummingbird to hover in flight. Argentinosaurus had it too. Pneumatic chambers running through its massive vertebrae. The same basic design scaled up to support the largest body that ever walked on land. The same egg-laying reproductive strategy. The same colonial nesting behavior. The same fast early growth rates. All shared between this 70-ton titan and the sparrows outside your window. Because Argentinosaurus was a dinosaur, and birds are dinosaurs, the only lineage that survived. Distant cousins, yes, separated by 95 million years and an almost incomprehensible difference in size. But cousins nonetheless. This is the story we're going to tell. How the largest land animal that ever existed lived, fed, reproduced, and died in the warm floodplains of late Cretaceous Patagonia. We'll learn how it was hunted by pack-hunting predators nearly as long as a bus, and how it shaped entire ecosystems simply by existing. We'll contemplate how it connected across millennia to creatures still alive today. So settle in, relax, and let's travel back 95 million years to learn about the largest land animal to ever walk the earth. This is Argentinosaurus. Imagine, if you will, a world nearly 100 million years in the past. The late Cretaceous period, a time when the continents were still drifting into their modern positions, when flowering plants were just beginning to color the landscape, and when some of the most magnificent creatures ever to walk the earth moved slowly beneath ancient skies in what we now call Patagonia, that windswept region at the southern tip of Argentina. There lived a giant among giants. Argentinosaurus. Argentinosaurus lived roughly 94 to 97 million years ago. Take a moment to contemplate that span of time. Nearly 100 million years separates us from this animal, a gulf of time so vast it becomes almost meaningless to our everyday minds. And yet, here we are, able to piece together its story from fragments of bone turned to stone. The titanosaurs, the group to which Argentinosaurus belonged, were among the last of the great long-necked dinosaurs. By the late Cretaceous, they had evolved into some of the largest land animals that would ever exist. They were the culmination of millions of years of sauropod evolution, the final chapter in a story that had begun in the Triassic period, over 150 million years before Argentinosaurus walked the earth. Now, let's talk about size. When we say Argentinosaurus is often cited as the largest land animal ever known, what do we really mean? Most technical estimates place this dinosaur at about 30 to 35 meters. That's roughly 98 to 115 feet from head to tail. Some popular reconstructions have pushed that upper limit even further, suggesting lengths up to around 36 to 40 meters, 120 to 130 feet. But these more generous estimates are less widely accepted among paleontologists. The scientific consensus tends to favor the more conservative range. Picture, if you can, a creature longer than a blue whale, longer than 3 school buses placed end to end, a living thing so vast that as it moved, the ground itself would have trembled. But length is only one dimension of this giant. Standing height at the shoulders or hips has been reconstructed at around 12 to 14 meters. That's 39 to 46 feet. Imagine looking up at something as tall as a 4 or 5-story building. A living building that breathes, that moves, that exists. The torso alone, the distance from hip to shoulder, has been estimated at roughly 7 meters, about 23 feet long. And that torso was deep, profoundly barrel-shaped, a massive chamber necessary to house the digestive system of such an enormous herbivore. And then there's the question of weight. This is where things become particularly interesting and particularly uncertain. Early reconstructions gave Argentinosaurus a mass of about 80 to 100 metric tons, immediately placing it among the heaviest dinosaurs ever discovered. But as methods improved and new studies emerged, the estimates began to shift. Later research using different statistical and volumetric methods has produced a broad range, roughly 60 to 96 metric tons. That's a span of 36 tons, a difference equal to the weight of several adult elephants. Such is the challenge of reconstructing an animal from incomplete remains. Through the 2010s and into the early 2020s, a series of revisions by Gregory Paul and other researchers gradually converged on a narrower window, about 65 to 75 metric tons as a reasonable working estimate for a large adult Argentinosaurus. Many paleontologists now favor a figure around 70 to 75 metric tons as the most likely. Yet even today, some mass calculations, including volumetric models based on museum reconstructions, still return values in the low 80-ton range. Modern methods, for all their sophistication, do not fully agree. Why such uncertainty? The answer lies in what we have and what we don't. Only a limited set of bones are known, mainly vertebrae and parts of the limbs. No skull, no complete spine, no full skeleton laid out in stone, waiting to tell us its secrets. To estimate the size of Argentinosaurus, scientists must scale up from related titanosaurs with more complete skeletons. They take measurements from the bones we do have, compare them to better preserved cousins, and extrapolate. It's careful, meticulous work, but it requires assumptions. Different techniques produce different results. Bone circumference formulas, which estimate mass based on the thickness of limb bones, give one set of numbers. Three-dimensional volume models, which attempt to reconstruct the entire body digitally, give another. Assumptions about how bulky the body was, how much soft tissue surrounded those bones, add another layer of variation. This is why published numbers for Argentinosaurus span tens of metric tons, rather than converging on a single fixed value. We're not dealing with a living animal we can weigh. We're dealing with pieces of stone and the mathematics of reconstruction. The body of Argentinosaurus followed the classic sauropod design, a blueprint perfected over millions of years, a long neck extending upward and outward like a crane, allowing it to reach vegetation other animals could only dream of. That massive, barrel-shaped body housing an enormous gut, a fermentation chamber where tough plant matter was slowly broken down, a long tail counterbalancing that extended neck, and 4 pillar-like legs, columns of bone and muscle supporting all that weight. Like other titanosaurs, Argentinosaurus was a high-browsing herbivore. Its teeth were simple, peg-like structures, not designed for chewing, but for stripping leaves and branches. The real digestion happened in that cavernous gut, where microbes worked tirelessly to extract nutrients from fibrous vegetation. And this brings us to an important question. Was Argentinosaurus truly the largest? The answer, honestly, is that we're not entirely sure. Science rarely deals in absolutes, and the title of largest land animal ever remains an open question. Consider Patagotitan, another titanosaur from Patagonia, a neighbor of Argentinosaurus, separated by a few million years. Patagotitan is the largest well-preserved dinosaur we know, with specimens reaching about 37 meters in length and weighing between 50 and 70 metric tons. Because we have more complete remains of Patagotitan, some scientists consider it a stronger candidate for the title. Then there's Dreadnoughtus, a fitting name for a fitting giant, and Puertosaurus, known from even more fragmentary remains than Argentinosaurus. And beyond the titanosaurs, we have the diplodocids, long, relatively lighter sauropods like Supersaurus, which stretch to incredible lengths, but with more slender builds. The truth is, we may never know with absolute certainty which dinosaur was the largest. The fossil record is incomplete by its very nature. Fossilization is a rare event requiring specific conditions. Most animals that ever lived left no trace. We're working with an incomplete library, with pages missing, chapters lost to time. But perhaps that uncertainty is part of what makes Argentinosaurus so captivating. It exists at the very edge of what's possible, at the theoretical limit of how large a land animal can grow before physics itself imposes constraints. So let's return to that ancient Patagonian landscape, 95 million years ago. The air is warm, the vegetation is thick, conifers, ferns, and the relatively new flowering plants. Somewhere in this landscape, an Argentinosaurus moves slowly through the forest. Each step is deliberate, careful. Despite its size, it moves with a certain grace, the grace of something perfectly adapted to its world. It reaches up with that impossibly long neck, stripping leaves from branches 30 feet above the ground. Its head moves among the canopy 12 meters up, 4 stories high, where no other creature can feed. It processes hundreds of pounds of vegetation each day, fuel for that enormous body. Around it, the Cretaceous world goes on. Smaller dinosaurs dart through the undergrowth. Pterosaurs soar overhead. In some distant ocean, mosasaurs hunt. But here, in this moment, there is only the giant, feeding, existing, living out its span of years in a world that no longer exists except in stone and imagination. This is Argentinosaurus, a titan of the late Cretaceous, a giant among giants, perhaps the largest land animal ever to walk the earth, or perhaps one of several that pushed against the very limits of what's possible. We may never know with complete certainty, but we know it existed. We know it walked and fed and lived in a world almost unimaginably distant from our own. And that knowledge, that connection across 95 million years, is itself a kind of wonder. Now let us consider something truly remarkable. How does a giant begin? Argentinosaurus, for all its enormity, started life in the most humble way imaginable, inside an egg. Sauropods were egg layers, as all dinosaurs were. And here we encounter one of nature's most astonishing transformations, the journey from egg to titan. Many of the details we're about to explore are inferred from other titanosaurs and sauropods, drawn from the better preserved relatives of Argentinosaurus. The numbers are approximate, best estimates rather than measurements. but they paint a picture that is no less extraordinary for its uncertainty. First, the egg itself. Work by Mark Hallett and Matthew Weddell has estimated that Argentinosaurus eggs were probably around 1 liter in volume. Picture that for a moment. About the size of a large grapefruit, only slightly larger than an ostrich egg. The diameter would have been somewhere in the range of 15 to 20 centimeters, small enough to hold comfortably in 2 hands. From an egg that size would emerge a hatchling no more than about 1 meter long, roughly 3 feet, weighing around 5 kilograms. That's about 11 pounds. A newborn Argentinosaurus could have fit in your arms. Pause and consider that transformation. From 5 kilograms to 60 or 70 metric tons. From 11 pounds to potentially 150,000 pounds. An increase of roughly 5 orders of magnitude. A multiplication by a factor of 10,000 or more. Few animals on Earth undergo such a dramatic change in size over their lifetime. No direct eggs or nests have been confidently assigned to Argentinosaurus specifically. We don't have that smoking gun, that perfect fossil of an Argentinosaurus nest, with eggs still inside. But titanosaur nesting sites that have been discovered show us the pattern. Shallow ground nests, scraped into the earth, containing clutches of many relatively small eggs, similar to other sauropods, similar to what we might expect from Argentinosaurus. How long did these eggs incubate? By analogy with large birds and using scaling models for dinosaur embryos, incubation for a 1 liter egg is often estimated at somewhere on the order of a few months, roughly 60 to 90 days. But this is model-based speculation, extrapolated from what we know of other creatures. We haven't measured it for Argentinosaurus. We can't. We can only reason our way toward likely numbers. Imagine those months. An egg buried in warm sand or soil, perhaps in a communal nesting ground where many Argentinosaurus had laid their clutches. The parent long gone, sauropods, as far as we can tell, did not tend their nests. Inside each egg, an embryo develops in darkness, curled tight, growing until the day it breaks free. And then, finally, emergence. A tiny creature, no bigger than a medium-sized dog, blinking in the Cretaceous sunlight. Vulnerable, alone, with no parent to protect it or teach it. Its survival depends entirely on instinct and luck. Like many ground nesting animals that produce large numbers of small offspring, reptiles, birds, even some mammals, titanosaurs probably relied on a strategy of quantity over quality. Lay many eggs. Accept that most hatchlings will not survive. Hope that a few, through chance or vigor, or both, will make it through the gauntlet of predators and disease and simple misfortune. Only a tiny fraction of Argentinosaurus hatchlings survived long enough to reach adulthood. Most would have been lost in those first weeks, months, years, picked off by predators, succumbing to illness, failing to find enough food. The mortality rate was likely staggering, but for those that survived, for the lucky few, what followed was growth on a scale almost difficult to comprehend. Sauropod bone histology, the microscopic study of bone structure, tells us that these animals grew extraordinarily rapidly. Some large sauropods reached near adult size in just a few decades. Estimates for big titanosaurs often fall in the range of roughly 20 to 40 years to reach full size. 20 to 40 years. In that span, an Argentinosaurus would transform from a 5-kilogram hatchling to a 70,000 kilogram adult. That's an average weight gain of thousands of pounds per year, year after year, for decades. To sustain such growth required constant feeding, an appetite that must have been nearly insatiable. Young Argentinosaurus were eating machines, processing vast quantities of vegetation, converting plant matter into bone and muscle and sinew at a rate that demanded an elevated metabolism, not cold-blooded and slow like a crocodile, but something more active, more bird-like, a metabolism that burned hot to fuel that relentless growth. Imagine a juvenile Argentinosaurus at age 10, perhaps already 10 or 15 meters long, several tons in weight, but still growing, still hungry, still years away from its full size. It would have been an awkward in-between creature, neither small nor yet truly giant, navigating a world full of danger even as it slowly outgrew most threats. And then, eventually, maturity. Growth would slow. Not stop entirely, perhaps. Many reptiles continue growing throughout their lives, though at decreasing rates, but slow dramatically. The years of ravenous consumption would give way to a steadier existence. An adult phase, long and relatively stable. Histological studies on other large sauropods suggest total lifespans that could reach 60 to 80 years or more, perhaps even longer. Argentinosaurus is usually assumed to fall within a similar range, 6 to 8 decades, if fortune smiled. Most of those years spent as an adult, after the frenetic growth of youth had passed. Picture then the full arc of an Argentinosaurus life. It begins in an egg no larger than your fist, incubating for months in the Patagonian soil. The hatchling that emerges is tiny, vulnerable, with survival odds that are vanishingly small. Most of its siblings will die. Most of its generation will never see their first year. But this one, this particular Argentinosaurus, survives. It feeds constantly through its youth, growing at a pace that seems almost impossible. By its 20th year, it's already approaching full size, already one of the largest creatures in its world. By 30 or 40, growth has slowed. It has reached its full dimensions, 30 meters long, 70 tons in mass, a giant among giants. And then, if it's lucky, if it avoids injury, disease, drought, all the countless hazards of existence, it lives on. For decades more, moving through its Cretaceous landscape, feeding, existing, perhaps breeding, adding its own eggs to some future nesting ground, until finally, at 60 or 70 or 80 years of age, it stops. Its body falls. The earth reclaims it. And in time, in deep geological time, a few of its bones become stone. This is the life cycle we've pieced together from fragments and inference, from egg to hatchling, to juvenile to adult to death, from 5 kilograms to 70,000, from 3 feet to 110. It's a story told in probabilities and estimates, in comparisons to related species and mathematical models. But it's a story nonetheless, the story of how a giant lived from beginning to end. Let us now turn our attention to a fundamental question. What does a giant eat? When you weigh 60 to 70 metric tons or more, when your body burns through energy simply by existing, simply by maintaining that enormous mass against the pull of gravity, what sustains you? For Argentinosaurus, the answer was plants. Only plants. An herbivorous sauropod, it ate a wide variety of vegetation, from the highest tree foliage to lower growing plants in its late Cretaceous environment. Its entire existence revolved around the simple, endless task of finding food, consuming it, and converting it into the energy needed to power that titanic body. The late Cretaceous landscape of Patagonia was, fortunately, rich with options. We know this from the fossil pollen preserved in the Winkle Formation, the same ancient rock layers that hold the bones of Argentinosaurus itself. These microscopic grains tell us what plants were growing there 95 million years ago, painting a picture of the menu available to a hungry giant. the vegetation was diverse. Ferns carpeted the understory. Liverworts and hornworts grew in damp places. Gymnosperms, that ancient lineage that includes conifers and netophytes, stood tall, their needle-like leaves and tough branches resilient and fibrous. And alongside them, something relatively new in Earth's history: flowering plants, angiosperms, adding their own variety to the mix. Conifers and other tough, fibrous plants were probably important food sources for Argentinosaurus. These weren't tender, easily digestible greens. They were resilient, woody, full of cellulose and lignin, compounds that resist breakdown. But Argentinosaurus, like all giant sauropods, had evolved ways to handle such fare. And there were other options too. The leaves and shoots from flowering plants, perhaps fruits and seeds when available, a diverse browse from the full spectrum of the ecosystem. Now, imagine the act of feeding itself. Argentinosaurus had a small head, surprisingly small for such an enormous body, equipped with simple peg-like teeth. These teeth weren't designed for chewing, for grinding food into a pulp the way our molars grind. They were stripping tools, meant to rake vegetation from branches, to pull leaves free, to gather plant matter quickly and efficiently. The real processing would happen elsewhere, deep in that massive gut. That long neck, stretching perhaps 10 meters or more, was both a tool and a marvel of engineering. It allowed Argentinosaurus to sweep through a wide feeding area without having to move its entire body. By raising its neck, it could reach high branches that no other herbivore could access. By lowering it, and there's evidence that sauropods could lower their necks quite effectively, it could feed on vegetation closer to the ground. Picture the motion, a slow, deliberate sweep, the head moving along a branch, those peg-like teeth stripping leaves as it goes. Then another branch, another tree, the neck swaying gently, almost hypnotically, as it works its way through the canopy. But here's the challenge. How much did it need to eat? The answer is staggering. Because of its enormous size, 60 to 70 metric tons or more, Argentinosaurus would have needed very large quantities of foliage each day. Some estimates exceed several hundred kilograms of plant matter daily. Several hundred kilograms. That's upward of 600 or 700 pounds of vegetation every single day, just to maintain that body. Half a ton of leaves and branches and shoots, processed from sunrise to sunset. And this was relatively low nutrient food, not calorie dense like meat, not easily digestible like the grasses that would evolve much later. These were tough, fibrous plants, conifers with their resinous needles, woody branches, cellulose-heavy ferns. Getting enough energy from such food required eating almost constantly. The secret lay in the gut. Like other giant sauropods, Argentinosaurus likely relied on a huge, slow-working digestive system, a massive fermentation chamber housed in that barrel-shaped torso we discussed earlier. 7 meters from hip to shoulder, remember, and deep, profoundly deep. Inside that gut lived countless microorganisms, bacteria, archaea, perhaps fungi, all working to break down the plant matter that Argentinosaurus consumed. Fermentation is a slow process, requiring time and the right conditions. The food would have moved through the system gradually, spending days in that internal cauldron, while microbes extracted every possible calorie. This is how giant herbivores work, not through efficient, rapid digestion, but through sheer volume and time. Eat constantly, process slowly, extract enough energy to survive, even if the efficiency is low. Think of a cow with its multiple stomach chambers, endlessly chewing its cud. Now scale that up 100-fold. That was Argentinosaurus. There's something almost meditative about imagining its days. Dawn breaks over the Cretaceous landscape. Argentinosaurus is already feeding. It may have fed through the night, or perhaps it rested and now resumes with the light. The neck rises, reaches, strips leaves from a stand of conifers. Hours pass. The sun climbs, still feeding, midday. The heat is significant, but Argentinosaurus continues its slow progress through the forest, moving from tree to tree, occasionally lowering its neck to browse on lower vegetation, then raising it again to reach the canopy. Afternoon, more feeding. The act is mechanical, repetitive, necessary. There's no time for much else. With such enormous energy requirements, life becomes a nearly continuous process of consumption. Evening. The light begins to fade. Perhaps now Argentinosaurus rests, its gut working through the day's intake. Or perhaps it continues feeding, processing vegetation in the growing darkness, driven by the endless need to fuel that colossal body. This was the rhythm of its existence. Find food, strip it from branches, swallow it, let the gut do its slow work, move on to the next tree, the next stand of vegetation, repeat, day after day, year after year, decade after decade. It's not a glamorous existence. There are no dramatic hunts, no clever strategies, just the simple, patient labor of eating, of converting the ancient forests of Patagonia into the living mass of the largest land animal that would ever walk the earth. But there's a certain grandeur to it nonetheless, a quiet dignity in that endless feeding, because this simple act, this daily consumption of hundreds of kilograms of plant matter, is what allowed something as impossibly large as Argentinosaurus to exist at all. The plants fed the giant shaped the landscape. As it moved and fed, it opened up the canopy, allowed light to reach the forest floor, spread seeds in its droppings, created pathways through the vegetation that other animals would follow. It was, in its way, a living force of nature, a creature whose very existence altered the world around it. And all of it, all of that impact, all of that presence was powered by leaves. Simple, tough, ancient leaves, stripped from branches by peg-like teeth, fermented in a barrel-shaped gut, converted into the energy needed to sustain 70 tons of living dinosaur. This is how a giant eats, not with drama or violence, but with patience, with constancy, with the slow, inevitable persistence of something too large to hurry, too massive to be anything other than exactly what it is. A herbivore, a browser, a converter of plants into presence. This was Argentinosaurus, feeding in the forests of the late Cretaceous, one mouthful at a time. To understand Argentinosaurus, we must step back and see where it fits in the grand sweep of time, in the story of sauropods, in the story of dinosaurs, in the story of life on Earth. This is not a creature from the dawn of the dinosaur age. By the time Argentinosaurus walked the Earth, dinosaurs had already ruled for well over 100 million years. Sauropods, those long-necked giants, had already risen, diversified, and in some lineages, declined. Argentinosaurus represents something specific, one of the last, largest stages in sauropod evolution, a culmination, perhaps even a finale. Let's place it in time first. Argentinosaurus lived in the late Cretaceous, specifically during the Cenomanian and Chironian ages, roughly 96 to 92 million years ago, depending on the source. This is what paleontologists sometimes call the mid-Cretaceous slice of the late Cretaceous, a period when the world was warm, sea levels were high, and the continents were continuing their slow drift away from the ancient supercontinent of Gondwana. Its fossils come from the Huincul Formation in what is now Neuquén Province, Patagonia, Argentina. This was a fluvial system, a landscape dominated by rivers, floodplains and channels. The sediments that would eventually become rock were laid down by flowing water, burying the bones of the creatures that lived and died along those ancient waterways. The Huincal Formation preserves a rich dinosaur fauna. Argentinosaurus was not alone. Giant predators like Mapusaurus prowled the same landscape, themselves enormous theropods that may have hunted in packs. Other herbivores, other theropods, a complete ecosystem frozen in stone. But Argentinosaurus was the giant among giants in this world. Now let's consider its place in the evolutionary tree. Argentinosaurus belongs to Titanosauria, the dominant sauropod group of the Cretaceous period. By the time titanosaurs emerged, many of the earlier sauropod lineages that had ruled the Jurassic, the diplodocids with their whip-like tails, the towering brachiosaurs, had declined or disappeared entirely. The titanosaurs took their place and, in many ways, exceeded them. This group includes several of the largest land animals ever known. Argentinosaurus, yes, but also Patagotitan, Dreadnoughtus, Puertosaurus and others. The titanosaurs became the undisputed masters of the herbivore niche in the Cretaceous, spreading across the fragmenting continents of the former Gondwana. Within the titanosaurs, Argentinosaurus is usually classified as a very large, fairly basal member, meaning it's not one of the most heavily armored or highly specialized forms, but rather represents a more generalized body plan taken to an extreme of size. Different analyses place it either just outside the more advanced Lithostratian titanosaurs or within a giant-bodied group of South American colossosaurians. The details shift as new studies emerge and new techniques refine the family tree, but the broad picture remains consistent. Argentinosaurus was a titanosaur, and a remarkably massive one. Its huge size illustrates what might be called a late peak in sauropod gigantism. The story of sauropods is, in many ways, a story of increasing size over geological time, though not a simple, linear progression. Let's trace that story briefly. In the Triassic and early Jurassic, the ancestors of sauropods, the sauropodomorphs, started small. Some were bipedal, walking on two legs, herbivorous but modest in size. Over time, they grew larger, adopted a four-legged stance, lengthened their necks. By the Jurassic, the classic long-necked sauropods had emerged and diversified spectacularly. Diplodocus, with its extraordinarily long tail and relatively light build. Brachiosaurus, with its giraffe-like posture and forelimbs longer than its hind limbs. Apatosaurus, Camarasaurus, a whole menagerie of giants, each adapted to its particular niche. These Jurassic sauropods were already enormous, some reaching lengths of 25 to 30 meters, masses of 20 to 40 tons or more. They seemed to represent a kind of maximum, a ceiling on how large a land animal could grow, but they weren't the end of the story. In the Cretaceous, the titanosaurs emerged and pushed that ceiling even higher. Studies of sauropod body evolution showed that Cretaceous titanosaurs evolved specific adaptations for bearing enormous mass, broader chests, more robust forelimbs, a weight distribution that shifted more mass onto the front legs, better suited to supporting truly colossal bodies. Argentinosaurus is one of the key examples used in reconstructions of maximum land animal size, a living test of what's physically possible for a terrestrial creature. Its body represents the culmination of over 150 million years of sauropod evolution, a lineage that kept asking the question, how large can we become? And the answer in Argentinosaurus was this large. possibly no larger. Its existence in South America reflects the geography of the time. Once, the supercontinent Gondwana began to fragment, breaking apart into what would become South America, Africa, India, Antarctica, and Australia. Sauropod evolution began to diverge on these separated landmasses. Different titanosaur lineages evolved in isolation, adapting to their local conditions. Titanosaurs became especially diverse and gigantic in what is now South America, Africa, and India. South America, in particular, seems to have been a hotspot for truly colossal forms. Argentinosaurus, Patagotitan, Dreadnoughtus, Puertosaurus, all South American, all pushing the upper limits of size. Why South America produced so many giants is still a matter of research and debate. Perhaps the vegetation was particularly abundant. Perhaps the lack of certain predators allowed herbivores to grow larger. Perhaps it was simply chance, the right lineages in the right place at the right time. Whatever the reason, Patagonia in the late Cretaceous was home to the largest land animals that would ever exist. In the broader timeline of sauropods, Argentinosaurus appears tens of millions of years after those iconic Jurassic giants. Diplodocus last walked the Earth around 145 million years ago, at the end of the Jurassic. Brachiosaurus lived roughly 150 million years ago. By the time Argentinosaurus emerged, these animals had been gone for 50 million years, a span longer than the entire Cenozoic era, longer than the time separating us from the extinction of the non-avian dinosaurs. And yet, sauropods persisted. They didn't just survive into the Cretaceous, they thrived, they diversified. And in the tyrannosaurs, some lineages reached even greater sizes than their Jurassic predecessors. Argentinosaurus is proof that sauropods were not in decline in the Cretaceous. They were, in some ways, at their peak. This is where Argentinosaurus sits, at the end of a long evolutionary story, but not at a decline, at an apex. A relatively advanced titanosaur in a group that had taken over from earlier sauropod lineages. A creature of the late Cretaceous, living in a world that would continue for another 30 million years before the asteroid struck and changed everything. One of the last of the truly gigantic sauropods, and quite possibly the largest land animal that ever lived. It represents a kind of culmination, the answer to a question that evolution had been asking for over 100 million years. How large can a land animal become? And in Argentinosaurus, evolution seems to have found its limit. Not because the lineage died out immediately. Titanosaurs would continue for tens of millions of years after Argentinosaurus, but because something about the body plan, the environment, the physics of being a land animal seems to have imposed a ceiling somewhere around this size. Argentinosaurus approached that ceiling, perhaps touched it, perhaps slightly exceeded it. And then, 66 million years ago, the Cretaceous ended. An asteroid struck what is now the Yucatan Peninsula. The skies darkened, the food chains collapsed, and the non-avian dinosaurs, including all the remaining titanosaurs, vanished from the Earth. The age of giants ended, but for 30 million years before that catastrophe, Argentinosaurus and its kin had walked the Earth as living monuments to what evolution can achieve given enough time, enough space, and enough opportunity. They were the culmination of the sauropod story, the final chapter in a narrative that began with small bipedal animals in the Triassic and ended with 70-ton titans in the late Cretaceous. This is where Argentinosaurus belongs in the grand timeline, near the end, but at the height, the last of the giants and the largest of them all. Now let us reconstruct the world in which Argentinosaurus lived Not the world as it is today, dry, windswept Patagonian scrubland, beautiful in its starkness, but nothing like what existed 95 million years ago. We need to travel back to see the landscape as it was, a warm, lush, dynamic environment dominated by rivers and life. This is the world of the Huincal Formation, preserved now in the rocks of Neuquén Province, Patagonia, but once a living, breathing ecosystem in the mid-late Cretaceous, roughly 97 to 93.5 million years ago. The Cenomanian to early Turonian ages, to use the technical terms. Picture first the basic geography, a vast river system, not a single stable channel, but a braided river, multiple channels weaving and splitting and rejoining, constantly shifting across a broad floodplain. Sandbars emerging and disappearing with the seasons. Islands of vegetation growing up wherever the land stayed dry long enough. Water flowing, always flowing, carrying sediment from distant highlands down toward an ancient sea. The Neuquén Basin was a large, low-lying area where this river system spread out, depositing sand and silt in layers that would, over millions of years, become the sandstone and siltstone we find today. Within those layers, the bones of the creatures that lived and died along these rivers. The rocks tell us the story. Channel deposits where fast-moving water once flowed. Bar deposits where sediment piled up during floods. Overbank deposits, the fine silt and mud that settled when rivers overtopped their banks and spread across the floodplain. This was not a static landscape. It was dynamic, ever-changing, shaped by the rhythms of water and season. The climate was warm, warmer than modern Patagonia by far. Warm to subtropical, with no prolonged freezing, no winter ice. The late Cretaceous was globally a warm period in Earth's history. Sea levels were high. The poles lacked ice caps. And even at the latitude of Patagonia, which was somewhat farther south than it is today due to continental drift, the climate was mild and hospitable, but it wasn't uniformly wet. The climate was likely seasonal, with distinct intervals of heavy rain and drier periods. During the wet season, the rains would come, sometimes gentle, sometimes torrential. The rivers would swell, overflowing their banks, spreading across the floodplain in broad sheets of muddy water. Channels would shift, cutting new paths, abandoning old ones. What had been dry land 1 month might be underwater the next. Then the dry season would arrive. River flow would decrease. Channels would narrow. Sandbars and floodplains that had been submerged would emerge, drying in the sun, becoming accessible again to the creatures that depended on them. This seasonal rhythm, flood and drought, wet and dry, created a dynamic mosaic of habitats. No 2 years quite the same. No single location stable for long. And yet, despite or perhaps because of this dynamism, life was abundant. The floodplains and river margins supported diverse plant life. Ferns unfurled their fronds in the understory, thriving in the moist soil. Conifers stood tall, ancient lineages that had dominated forests for hundreds of millions of years. Cycads, those palm-like plants that dinosaurs had been eating since the Triassic, grew in scattered groves. And alongside them, something new. Flowering plants, angiosperms, still relatively early in their evolutionary history, but already diversifying rapidly. They added their own variety to the mix, different leaf shapes, different growth strategies, different ways of thriving in this flood-prone environment. The vegetation existed in layers. Tall coniferous trees formed a canopy in the more stable, forested patches along the rivers, places where the ground stayed dry enough for trees to establish deep roots. Below them, a mixed understory of smaller trees, shrubs, ferns, cycads, creating a complex, three-dimensional habitat. In more open areas, places that flooded frequently or where the soil was sandier, the vegetation was lower, adapted to periodic burial and exposure. Shrubs that could regrow from buried stems. Plants with seeds that could survive being washed downstream and deposited in new locations. It was a rich, productive environment, providing abundant browse at different heights. Perfect, in other words, for giant sauropods. Argentinosaurus was not alone in this world. The Huincal Formation preserves a rich vertebrate fauna, a snapshot of an entire ecosystem. And what an ecosystem it was. Giant predators prowled the floodplains. Mapusaurus, a massive carcharodontosaurid theropod, perhaps the largest predator in this environment. Some paleontologists have suggested that Mapusaurus may have hunted in groups, coordinated packs, taking down prey far larger than any individual could handle alone. Whether this is true remains debated, but the possibility is tantalizing. Social hunters pursuing the largest land animals on Earth. Other theropods were present too. Abelisaurids, those strange, short-faced predators characteristic of the southern continents. Noasaurids, smaller and more lightly built. A range of carnivores, from the massive to the modest, each occupying its own niche in the food web. And there were other herbivores, other sauropods, though none quite matching Argentinosaurus in size. Iguanodont-type dinosaurs, the ornithopods, stocky herbivores that browsed on vegetation closer to the ground, filling the role that ceratopsians would play in the northern continents. The rivers themselves teemed with life. Crocodilians, some of them large and formidable, lurking in the channels and along the banks. Turtles, both aquatic and semi-aquatic. Fish of various sizes, forming the base of the freshwater food chain. It was a complete, functioning ecosystem, productive, diverse, with energy flowing from plants to herbivores to carnivores, with scavengers and decomposers recycling the dead back into the soil. And through this world moved Argentinosaurus. Imagine it. Dawn breaking over the floodplain. The air is humid, warm. Mist rises from the river channels. Somewhere in the distance, the call of a theropod, low, resonant, carrying across the water. Argentinosaurus stands in a grove of conifers, already feeding. Its long neck reaches up into the canopy, stripping needles from branches 20 meters above the ground. Around it, the forest shows signs of its feeding. Trees with lower branches stripped bare, the understory trampled by those pillar-like legs. Later in the day, it might move toward the river to drink. A careful approach. Even a giant must be cautious near water where crocodilians wait. The river is wide here, slow-moving, the water murky with suspended sediment. Argentinosaurus lowers its head, drinks deeply, then moves on. As the dry season progresses, the floodplain becomes more accessible. Argentinosaurus can range more widely, finding new feeding areas, browsing on vegetation that had been underwater months before. But the giant must always be aware. Mapusaurus and other predators are out there, perhaps watching, perhaps waiting for a moment of vulnerability. The rivers shaped everything in this environment. They brought water, essential for life. They brought nutrients, fresh sediment deposited with each flood, enriching the soil. They created the diverse habitats, channels, bars, floodplains, forested patches that supported such a variety of life. But they also brought danger. Frequent flooding and channel migration meant that animals could be caught by sudden rises in water level, trapped in channels buried by sediment. This is paradoxically why we know about Argentinosaurus at all. because occasionally these flooding events killed and buried large animals, preserving them in the sediment that would become the Huincal Formation. Death in the river system became millions of years later a window into life in the late Cretaceous. This was the world of Argentinosaurus, dynamic, productive, dangerous and alive. A warm seasonal floodplain dominated by braided rivers, forests of conifers and cycads, punctuated by open areas where shrubs and ferns grew, wet seasons that transformed the landscape, dry seasons that made it accessible again, a diverse community of herbivores and carnivores, of river dwellers and land walkers, all interconnected in the web of life. And moving through it all, the largest land animal that would ever exist, feeding on the abundant vegetation, drinking from the rivers, leaving massive footprints in the sand and mud, shaping the environment simply by existing within it. For a few million years, this world persisted. Then geological changes, climate shifts, the slow march of time, the Huincal Formation stopped being deposited. New environments replaced this one. The rivers changed course or dried up. The specific assemblage of species that included Argentinosaurus moved on or went extinct. But for that window of time, 97 to 93.5 million years ago, this was the world, and in its rivers and floodplains, a giant walked. Let us now meet some of the neighbors, the other creatures that shared this world with Argentinosaurus. The Huincal Formation preserves not just fragments of the largest land animal ever, but an entire community, a cast of characters, if you will, each playing its role in this ancient ecosystem, from the apex predators to the smallest hunters, from fellow giants to more modest herbivores. This was a world of remarkable diversity. First, the predators, because in any ecosystem, the carnivores shape the lives of everything else. At the top of the food chain stood Mapusaurus, a giant carcharodontosaurid theropod comparable in size to its famous relative, Giganotosaurus. Picture a predator 12 meters long or more, weighing perhaps 4 to 5 tons, with massive jaws lined with serrated teeth designed for slicing through flesh. Mapusaurus was one of the top predators in Argentinosaurus's ecosystem, perhaps the top predator. And here's what makes it particularly intriguing. Multiple Mapusaurus specimens have been found together, leading some paleontologists to suggest they may have been social hunters, working in coordinated groups. Imagine that for a moment. A pack of Mapusaurus moving through the conifer forests, communicating with low calls, coordinating their approach toward an Argentinosaurus. Not a single predator trying its luck, but multiple animals working together, capable of bringing down even the largest prey. It's a hypothesis, not a certainty, but the possibility adds a layer of drama to this ancient world. But Mapusaurus was not alone in the predator guild. The Huincal Formation preserves several abelosaurid theropods, those distinctive short-faced predators that were characteristic of the southern continents. Scorpia venata, whose name means scorpion hunter, was a medium-sized member of this group, not as massive as Mapusaurus, but still formidable, perhaps 9 meters long, built for power rather than speed. And there was Ilocalesia, another abelosaurid, part of what paleontologists call a diverse mid-sized predator guild. Multiple predator species, overlapping in size and habitat, each presumably specialized in slightly different ways to reduce competition. Perhaps one preferred hunting near the rivers, another in more open areas. Perhaps one targeted younger sauropods, another focused on ornithopods. The details are lost to time, but the diversity itself tells us something important. This ecosystem was productive enough to support multiple large predators simultaneously. Smaller predators filled their own niches. Winklesaurus, a small noasaurid theropod, represented the small predator layer of the ecosystem. These were the hunters of smaller prey, the creatures that went after lizards, small mammals, perhaps juvenile dinosaurs. Lightly built, quick, occupying a completely different world from the giants around them. Oviraptor, a Paravian theropod closely related to the bird lineage, adds another dimension. These were the dinosaurs most closely related to modern birds, and they brought bird-like hunting strategies to this ancient landscape. Perhaps they were more intelligent, more agile, filling ecological roles that would later be occupied by actual birds. And there were others: Orniraptor, Gualicho, additional theropod dinosaurs from the Winkle Formation, each adding to the variety of predatory niches. The exact relationships and roles of some of these animals are still being worked out, but their presence speaks to a complex, layered ecosystem where predation happened at many scales. Argentinosaurus was not the only giant herbivore in this world. It shared its environment with other sauropods, though none matched its colossal size. Choconsaurus, a titanosaurian sauropod, a relative in other words, lived alongside Argentinosaurus. It was smaller and more completely known from fossils, giving us a clearer picture of what a typical large titanosaur looked like. Still enormous by any reasonable standard, but dwarfed by Argentinosaurus, and there were sauropods from different lineages entirely. Cathartosaura and Limasaurus, both rebecasaurid sauropods, represented a different branch of the long-necked dinosaur family tree. Rebecasaurids had their own distinctive features: different tooth shapes, different neck proportions, different feeding strategies. This matters because it meant these sauropods weren't all competing for exactly the same resources. Argentinosaurus, with its extreme height and reach, could access vegetation that was simply unavailable to others. The Rebecasaurids, with their different dental and neck anatomy, may have specialized in different types of plants or different feeding heights. Multiple giant herbivores could coexist because they partitioned the resources, each taking a slightly different slice of the available food, and there were herbivores of more modest proportions. Several iguanodont-type ornithopods are recorded from the Winkle Formation. These were medium-sized herbivores, stocky, quadrupedal, or semi-bipedal dinosaurs that browsed on vegetation closer to the ground. They filled a role similar to what ceratopsians like Triceratops would fill in the northern continents, though they were from a completely different lineage. These ornithopods added yet another layer to the ecosystem structure. Where sauropods fed high and used their massive guts to process tough vegetation, ornithopods had different strategies: more complex teeth for grinding, perhaps more selective feeding, the ability to move more quickly and access different types of habitat. So picture now the full community. The floodplain at dawn, an Argentinosaurus feeding in a stand of conifers, its head moving among branches 12 meters above the ground. Nearby, a Choconsaurus, smaller but still impressive, browses on mid-level vegetation. Further off, a group of ornithopods moves through more open ground, grazing on ferns and low shrubs. At the river's edge, a Cathartosaura drinks cautiously, aware that crocodilians lurk in the murky water, and watching, always watching. A Mapusaurus, perhaps not alone, assessing the herbivores, looking for weakness, for opportunity. Elsewhere, a Scorpiovenator moves through the understory, its shorter face suited for a different style of hunting. In the trees, an Oviraptor rustles, pursuing something small and quick. This is a complete world. Producers and consumers, predators and prey, giants and small creatures, all interconnected. Energy flows from sunlight to plants, from plants to herbivores, from herbivores to carnivores. Scavengers clean up the dead. Decomposers break down the remains. Nutrients return to the soil, feed the plants, and the cycle continues. Each species plays its part. The giant predators keep herbivore populations in check, preventing overgrazing. The herbivores shape the vegetation through their feeding, creating openings in the forest, spreading seeds, maintaining the diverse plant community. The smaller predators control populations of smaller animals. The river system provides water and nutrients and creates the dynamic habitats that allow so many species to coexist. It's a balance, though not a static one. Populations rise and fall. Floods kill indiscriminately. Droughts stress the system. Predators sometimes go hungry. Herbivores sometimes fall to predation. Individual lives are brief, often brutal. But the ecosystem persists, adapting, continuing. For roughly 4 million years, this community existed. From about 97 to 93.5 million years ago, give or take, these species shared this landscape. Not every individual lived at the exact same moment, of course. Populations shifted, species evolved. The specific cast of characters changed subtly over those millions of years. But broadly speaking, this was the Huincle Formation ecosystem. Argentinosaurus and Mapusaurus, Choconsaurus and Scorpiovenator, Rebbachisaurids and ornithopods, small hunters and river dwellers, all living, feeding, reproducing, dying in the warm floodplains of late Cretaceous Patagonia. Then time moved on. The environment changed. New sediments buried the old. The animals of the Huincle Formation gave way to new communities, and eventually, 66 million years ago, the asteroid struck, and the age of non-avian dinosaurs ended entirely. But for those few million years, they had their moment. And in the rocks of Neuquén province, we can still read their story. Bones turned to stone, telling us who lived here, what they ate, how large they grew, how they died. A snapshot of an ancient world, preserved just well enough for us to glimpse what was. And at the center of it all, the largest land animal that would ever walk the earth. Not alone, but part of a community. Not isolated, but connected to every other creature in its ecosystem. Predator and prey, competitor and cohabitant. Giant among giants in a world that no longer exists. This was Argentinosaurus's world. These were its contemporaries. This was the community in which it lived and died 95 million years ago, in what is now Patagonia. Now let us consider how Argentinosaurus interacted with its world, not just as an inhabitant, but as a force that shaped the very ecosystem around it. When you are the largest land animal on Earth, your existence is never neutral. Every action has consequences. Every movement leaves an impact. And in a community as complex as the Huincle Formation, those impacts rippled outward, touching the lives of countless other creatures. First, the ever-present question: how did something so enormous defend itself? The answer, most likely, lies in the simple fact of size itself. An adult Argentinosaurus, healthy, fully grown, 70 tons of living muscle and bone, was probably nearly invulnerable. What predator, even one as large as Mapusaurus, would risk attacking such a creature? The physics are daunting. A single kick from those pillar-like legs could shatter bones. The sweep of that massive tail could crush. And simply the act of an Argentinosaurus turning, shifting its weight, moving an alarm, A predator caught in the wrong position could be trampled, killed by accident rather than intent. Healthy adult Argentinosaurus were, in all likelihood, poor targets, too dangerous, too much effort for too much risk. But not all Argentinosaurus were adults. The young, the juveniles, the calves, these were different prey entirely. Smaller, less experienced, not yet grown into that protective enormity. And this is where predators like Mapusaurus likely focused their attention. The edges of herds. That's where the vulnerable ones would be. A young Argentinosaurus that strayed too far from the group or lingered at the periphery became a target. Multiple Mapusaurus working together could potentially bring down a juvenile sauropod, something they could never accomplish with a full-grown adult. This predation pressure would have encouraged Argentinosaurus to stay in groups, to form herds for protection. There's safety in numbers, especially when the numbers include multiple adults whose sheer size creates a defensive perimeter. We don't have direct evidence of Argentinosaurus herding behavior, trackways showing multiple individuals moving together, or bone beds with many specimens preserved in one location. But the logic is compelling. Other sauropods show evidence of gregarious behavior. The presence of large pack-hunting theropods suggests strong predation pressure, and the basic mathematics of survival favor staying together. So picture them, a herd of Argentinosaurus, adults in the center or spread throughout, younger individuals protected within the group, all moving slowly through the floodplain, feeding as they go. A moving fortress of flesh, nearly unstoppable, deterring predators through collective mass. And when an Argentinosaurus did die, whether from predation, accident, disease, or old age, it became a resource that shaped the lives of many other creatures. A 70-ton carcass is an enormous amount of meat, far more than any single predator or group of predators could consume quickly. Such a resource would attract scavengers from across the landscape. The smaller theropods, abelisaurids like Scorpiovenata, noosaurids like Winklesaurus and Trochosaurus, these would have been among the first to arrive. Not large enough to take down living Argentinosaurus, but perfectly capable of tearing into dead flesh, gaining a massive temporary food source that could sustain them for days or weeks. Even smaller animals, early mammals, perhaps certain types of reptiles, insects, would eventually find their way to the carcass. Decomposers would begin their work. The nutrients locked in that enormous body would slowly return to the ecosystem, feeding the soil, enriching the floodplain, supporting new plant growth. One dead Argentinosaurus could feed dozens of animals over the course of its decomposition. Argentinosaurus nests, too, represented opportunities. We discussed earlier how titanosaurs laid many small eggs with high juvenile mortality. Those eggs, and the tiny hatchlings that emerged, would have been vulnerable to predation and scavenging. Smaller theropods could raid nests, consuming eggs or newly hatched young, gaining easy protein without the danger of confronting adults. This is brutal, but it's how ecosystems function. Energy flows from one organism to another, sometimes through predation, sometimes through scavenging, always seeking the path of least resistance. The movements of Argentinosaurus herds would have influenced behavior across the ecosystem. Imagine you're a medium-sized theropod, something like a Scorpiovenata. You learn, over time, that where the giant sauropods move, opportunities follow. Weakened individuals that can't keep up with the herd, sick or injured animals falling behind, the chaos of a herd moving through dense vegetation, disturbing smaller prey animals that then become easier to hunt, so you follow. At a safe distance, always wary of those massive legs, but following nonetheless. The Argentinosaurus herd becomes, in effect, a mobile hunting ground. And it's not just predators. Other herbivores, too, might have learned to associate with sauropod herds. Because where Argentinosaurus fed, they changed the environment in ways that created opportunities. Let's consider that impact more directly. By stripping high branches and trampling vegetation, Argentinosaurus opened up the forest canopy. Sunlight that had been blocked could suddenly reach the forest floor. New growth would sprout in these light gaps, fresh shoots, young plant, tender vegetation that other herbivores could then exploit. The iguanodonts, those medium-sized ornithopods, probably benefited from this. While Argentinosaurus focused on high browsing, feeding at heights of 10, 12, 15 meters where nothing else could reach, the ornithopods fed lower, on vegetation that was partly made accessible by Argentinosaurus's feeding patterns. This is called resource partitioning, and is how multiple herbivore species can coexist. They share the same habitat, but use it differently, reducing direct competition. Argentinosaurus takes the high brows. Rebecosaurids like Cathartisaura, with their different teeth and neck proportions, take mid-level vegetation. Ornithopods take the low brows, and everyone has enough. The physical impact of Argentinosaurus herds on the landscape itself would have been profound. Imagine a group of these giants moving through the braided river floodplains. Each step from those massive feet churns the soil, compacts the earth, creates depressions that will hold water during the next flood. Paths are widened, worn down by repeated passage. Trees are broken, some accidentally, as the herd moves through dense growth, others deliberately stripped of branches during feeding. Water flow patterns could change. A well-worn Argentinosaurus path might channel floodwater in new directions. Trampled areas might drain differently than vegetated ones. The landscape itself becomes, in part, a product of the giants that move through it, and plant patterns would shift in response. Some species might thrive in the disturbed soil that Argentinosaurus herds create, pioneer plants that specialize in colonizing trampled ground. Others might retreat to areas the herds avoid. Over time, over many generations, the plant community structure reflects the presence and movement of these enormous herbivores. And then there's the dung. Let's not be delicate about it. Argentinosaurus produced enormous amounts of waste. When you're consuming hundreds of kilograms of plant matter daily, much of it passes through relatively undigested. The result is massive piles of nutrient-rich dung deposited wherever the animal happened to be when nature called. This dung becomes its own resource. It fertilizes the soil, concentrating nutrients in specific locations. It feeds decomposers, beetles, fungi, bacteria that break it down and return those nutrients to the earth. And it attracts smaller herbivores and omnivores that forage in these nutrient-rich patches, either eating the dung directly, as many animals do, to extract remaining nutrients, or to gain beneficial gut bacteria, or feeding on the plants that grow especially lush in fertilized soil. An Argentinosaurus herd, over time, would create a patchwork of highly fertilized areas across the floodplain, indirectly supporting plant growth and creating feeding opportunities for animals that would never interact directly with the giants themselves. If Argentinosaurus formed mixed-age herds, adults and juveniles together, the dynamics become even more complex. Different age classes might have used slightly different feeding heights. Juveniles, with shorter necks, feeding lower. Adults reaching the highest branches. This would reduce in-group competition, members of the same species not fighting over the same resources, and would create multiple layers of impact on the vegetation. It would also change how Argentinosaurus herds overlapped with other herbivores. An ornithopod might avoid areas where adult Argentinosaurus were feeding, but might coexist more peacefully with juveniles that fed at similar heights. These are the subtle details, the nuanced interactions that make ecosystems complex and fascinating. And finally, consider the evolutionary dimension. The presence of immense titanosaurs like Argentinosaurus and very large theropods like Mapusaurus in the same formation is not coincidental. These sizes evolved in response to each other, in an arms race that played out over millions of years. As herbivores grow larger, they become harder to kill, creating selective pressure for predators to grow larger as well, to be able to tackle bigger prey. As predators grow larger and more dangerous, herbivores that are even bigger gain a survival advantage. Back and forth, push and pull, each driving the evolution of the other. Argentinosaurus represents one endpoint of this process. Gigantism pushed to an extreme, perhaps the largest a land animal can be while still remaining functional. And Mapusaurus represents the predator response, a theropod large enough and perhaps social enough to pose a threat even to such giants. They shaped each other's evolution, and in doing so, they shaped the entire ecosystem around them. This is the picture that emerges: Argentinosaurus as an ecological force, not just an animal living in an environment, but an animal that actively shaped that environment through its feeding, its movement, its waste, its death, its very existence. It created opportunities for other species. It modified vegetation patterns. It influenced predator behavior. It altered the physical landscape. It concentrated nutrients. It opened light gaps in forests. It trampled paths that other animals would follow. And it did all of this simply by being what it was: the largest land animal that would ever exist, living its life in the floodplains of late Cretaceous Patagonia. In ecology, we call these ecosystem engineers, species whose presence fundamentally changes the environment for other organisms. Elephants are ecosystem engineers in modern Africa. Beavers are ecosystem engineers in North American rivers. And Argentinosaurus, in its time and place, was an ecosystem engineer of extraordinary magnitude. Where it walked, the world changed. And for the 4 million years or so that it and its kind inhabited the Huincal Formation, the ecosystem bore the stamp of its influence, shaped by giants, structured by their feeding and movement, made richer and more complex by their presence. This is the fuller picture of Argentinosaurus, not just an individual animal, but a keystone species in its ecosystem, connected to every other creature through webs of interaction, predation, competition, facilitation, modification. A giant that mattered not just because of its size, but because of what that size allowed it to do and to be. This was Argentinosaurus in its world, massive, influential, integral, a creature whose absence, when it finally came, would have left a hole in the ecosystem as large as the animal itself. Every giant has its nemesis. For Argentinosaurus, that nemesis may have been Mapusaurus. In the same floodplains, at the same time, another giant moved, not a herbivore but a predator, a creature built for killing, armed with teeth like serrated blades, powerful enough to pose a threat even to the largest land animal on Earth. This is the story of hunter and hunted, played out at a scale almost impossible to imagine. Let us meet Mapusaurus properly. The name means earth lizard, derived from Mapu, the Mapuche word for earth, honoring the indigenous people of the region. The species name, Rosie, honors Rose Letwin, a donor who supported the research, so the full name, Mapusaurus rosie, connects this ancient predator to both the land it once walked and the people who helped bring its story to light. Its fossils were excavated over several years, from 1997 to 2001, in the Huincal Formation at a site called Cañadón del Gato in Neuquén Province, Argentina. The formal description came in 2006, published by paleontologists Rodolfo Coria and Philip Curry, the same Coria who had worked on Argentinosaurus years before. And what those fossils revealed was a predator of extraordinary size and capability. Mapusaurus was huge. Length estimates place it at about 10 to 12.5 meters, 33 to 41 feet from nose to tail. Mass estimates range around 3 to 6 metric tons, depending on the specimen and the methods used. That puts it close to Giganotosaurus in size, another famous South American giant and a close relative. To put that in perspective, Mapusaurus was larger than Tyrannosaurus rex, not by an enormous margin, but consistently larger, with a different body plan optimized for different hunting strategies. The skull was large and long-snouted, lined with blade-like serrated teeth. These weren't the bone-crushing teeth of T-Rex, designed to bite through anything. These were slicing teeth, meant to open massive wounds, to cut through flesh and cause catastrophic blood loss. Mapusaurus belongs to the family Carcharodontosauridae, the shark-tooth theropods, named for the resemblance of their teeth to those of sharks. This family includes some of the largest predatory dinosaurs ever discovered: Giganotosaurus from slightly earlier in Argentina, Carcharodontosaurus from North Africa, Acrocanthosaurus from North America. These were the apex predators of the southern continents in the Cretaceous, filling the niche that tyrannosaurs would occupy in the north. Mapusaurus lived in the same time and place as Argentinosaurus. The early, late Cretaceous, the late Cenomanian to early Turonian ages, roughly 97 to 93 million years ago. The same river floodplain environments of the Huincal Formation. The same warm, seasonally wet landscape with its rich dinosaur fauna. They walked the same ground, drank from the same rivers, moved through the same forests of conifers and ferns, and inevitably they encountered each other. Here's what makes Mapusaurus particularly intriguing: the bone bed. The site where Mapusaurus was discovered didn't yield just one individual. It contained remains of many individuals of different sizes, juveniles, subadults, adults, all found together in the same deposit. This is unusual for large theropods, which are often found as isolated individuals. But here were multiple Mapusaurus, apparently preserved together. Many paleontologists interpret this as evidence for at least some degree of group living or coordinated behavior. Perhaps they were social hunters, forming packs that worked together to bring down prey. Perhaps they congregated at a water source during a drought and died together. Perhaps they were drawn to a carcass and became trapped in the same flooding event that buried it. The exact interpretation remains debated, but the most tantalizing possibility is pack hunting. Multiple Mapusaurus working in coordination, communicating, strategizing, attacking as a group. And if that's true, it changes everything about how we imagine the interaction between Mapusaurus and Argentinosaurus. A single Mapusaurus attacking a healthy adult Argentinosaurus would be suicide. The size difference is simply too great. 70 tons versus 4 or 5. The sauropod would crush the theropod accidentally or deliberately, and that would be the end of it. But multiple Mapusaurus, that's a different calculation entirely. Picture it, a pack of 5 or 6 Mapusaurus, coordinating their movements, communicating with low vocalizations, having learned through experience how to hunt the largest prey on Earth. They've been tracking an Argentinosaurus herd for days, watching, waiting for an opportunity. And now they see it, a juvenile, perhaps 10 years old, already enormous by most standards, but still only a fraction of adult size. It's lingered at the edge of the herd, browsing on lower vegetation, while the adults moved ahead. The pack spreads out, surrounding the young Argentinosaurus on 3 sides, leaving one direction open, away from the herd, toward more open ground, where the sauropod's size becomes less of an advantage. One Mapusaurus moves in first, rushing from the side, jaws open, going for a leg. The Argentinosaurus bellows, tries to turn, but the terrain slows it. Another Mapusaurus attacks from behind, those serrated teeth sinking into the base of the tail, tearing away flesh, opening a massive wound. The juvenile tries to run, but it's already weakened, losing blood. The pack pursues, taking turns, each attack opening new wounds, each bite bringing the giant closer to collapse. It's brutal. It takes time, perhaps hours, but eventually, inevitably, the Argentinosaurus falls. This is speculation, of course. We weren't there. We can't know exactly how these interactions played out, but the evidence is suggestive. Mapusaurus in a bone bed, implying social behavior. Argentinosaurus living in the same ecosystem, the largest available prey. The physics of predation, which favor group hunting when prey is much larger than individual predators. And the teeth themselves, those blade-like serrated edges designed not for a single killing bite, but for slashing attacks that cause bleeding, that wear prey down over time. This is the hunting strategy of Carcharodontosaurids. Slice and retreat, attack and withdraw. Open wounds and let blood loss do its work. It's a strategy that makes more sense when multiple predators are involved, each contributing to the cumulative damage. Even if pack hunting wasn't the norm, even if it happened only occasionally or opportunistically, the presence of Mapusaurus would have shaped Argentinosaurus behavior. The threat was real. Juveniles were vulnerable. Even subadults might be at risk if they were sick, injured, or isolated from the herd. This would have created constant pressure to stay together, to remain vigilant, to protect the young. Adult Argentinosaurus might have positioned themselves around juveniles, creating a defensive formation. Herds might have avoided certain types of terrain, dense vegetation where predators could approach unseen, or narrow channels where escape was difficult, and there would have been moments of alarm. A sound in the forest, a scent on the wind, the sudden awareness that Mapusaurus was near. Perhaps the adults would vocalize, deep, resonant calls that carried across the floodplain, warning others, coordinating defensive positions. Perhaps they would stamp their feet, creating ground vibrations that communicated danger. Perhaps they would simply cluster together, a wall of flesh that no predator could penetrate. Mapusaurus, for its part, would have learned to be patient. You don't bring down a giant through recklessness. You watch, you wait, you look for weakness. A juvenile that strays too far, an adult that's visibly sick or injured, a herd that's stressed by drought, by lack of food, by some environmental pressure that makes them less vigilant. And when the opportunity comes, you strike, quickly, precisely, with whatever advantage you can muster. Perhaps alone, if the target is small enough or weak enough. More likely with others, if the prey demands it. This dynamic, predator and prey, hunter and hunted, was an apex predator in its ecosystem, sitting at the top of the food web. It competed with other theropods for resources, The abelisaurids and noosaurids, though smaller, would have taken some of the same prey. It navigated the seasonal rhythms of the floodplain, the floods and droughts that affected prey availability. It dealt with injury and illness, with the risks inherent in hunting dangerous prey. But when successful, when a hunt ended with a fallen Argentinosaurus, the reward was immense. Thousands of kilograms of meat, enough to sustain an individual Mapusaurus for weeks or a pack for days. And so, the cycle continued. Argentinosaurus feeding on vegetation, growing to enormous size as a defense against predation. Mapusaurus evolving larger body size and possibly social hunting to overcome that defense. Each species pushing the other toward extremes. This is the relationship we reconstruct from fossils and inference, Mapusaurus and Argentinosaurus, locked in an evolutionary dance. Not every encounter ended in predation. Most didn't. Most of the time, the Argentinosaurus were too large, too well defended, too alert. Most of the time, the Mapusaurus went hungry or settled for smaller prey. But sometimes, in the right circumstances, with the right target, with luck or skill or both, the hunt succeeded. And in those moments, when a Mapusaurus pack brought down a young Argentinosaurus, when those serrated teeth tore into 70-ton flesh, when the largest land animal on Earth fell to coordinated predation, in those moments, we see the drama of the Mesozoic at its most visceral. This is what it meant to be Argentinosaurus. To be hunted by one of the largest, most capable predators that ever lived. To live under constant threat. To defend yourself through sheer size and group coordination. To know that vulnerability meant death. And this is what it meant to be Mapusaurus. To hunt the largest prey on Earth. To risk everything in attacks that might fail or might succeed spectacularly. To exist at the knife's edge between starvation and feast. Two giants in the same ecosystem at the same time. One herbivore, one carnivore. One the largest land animal ever. The other among the largest predators ever. They shaped each other's evolution. They influenced each other's behavior. And in the floodplains of late Cretaceous Patagonia, their interactions, whether daily or rare, whether violent or merely tense, were among the most dramatic that the age of dinosaurs ever produced. This was the world of Argentinosaurus, a world where even the largest creatures were not entirely safe, where predation operated at scales we can barely imagine, where the fundamental dynamics of hunter and hunted played out between animals of extraordinary magnitude. And in the rocks of the Huincal Formation, we find evidence of both. The bones of Argentinosaurus, testament to the largest herbivore. The bones of Mapusaurus, testament to the predator that hunted it. Found together, preserved together, telling a story together. The story of giants in an ancient world, where size was both defense and target, where being the largest was both safety and vulnerability, where life and death operated on a scale that would never be seen again on land. This is the relationship between Argentinosaurus and Mapusaurus, hunter and hunted, locked in eternal opposition, frozen now in stone but once alive, breathing, moving through the same forests, drinking from the same rivers, existing in the same moment of deep time. Two names that will forever be linked in the story of the Cretaceous. The largest and the hunter of the largest. Argentinosaurus and Mapusaurus. Giant and nemesis. Prey and predator. Together, they tell us what it meant to be alive 95 million years ago, when the Earth was still a world of giants. How does a predator kill something 10 times its own weight? How does a pack of hunters bring down the largest land animal on Earth? We don't know for certain. We weren't there. No fossil preserves the moment of attack, the specific tactics, the precise choreography of predation at this scale. But we can reason our way toward plausibility. We can look at anatomy, at modern analogues, at the physics of predation. We can examine the bone bed evidence, the teeth structure, the environment. And from all of this, we can construct scenarios. Informed speculation, yes, but grounded in evidence and logic. Let us explore the possibilities. First, the fundamental assumption, group hunting. The Mapusaurus bone bed, multiple individuals of different ages found together, suggests some level of social or group behavior. Not every paleontologist agrees on the interpretation, but many consider it the most parsimonious explanation. And if Mapusaurus did hunt in groups, everything changes. What's impossible for one becomes plausible for several. What's suicidal alone becomes merely dangerous together. So picture a pack, 5, 6, perhaps 7 individuals. A mix of ages, large adults, subadults, maybe even larger juveniles learning the craft of hunting. They've been together for days, perhaps weeks, following a herd of Argentinosaurus across the floodplain. They're hungry. Individual hunts of smaller prey haven't been enough. They need something substantial. And they've identified a target. Target selection would be critical. Healthy adult Argentinosaurus, 70 tons, fully alert, surrounded by herd mates, would be near impossible targets. The risk would outweigh any potential reward. One wrong move, and a Mapusaurus gets crushed beneath those pillar-like legs. So the pack would look for vulnerability. Juveniles are the obvious choice, large enough to feed the entire pack for days, but only a fraction of adult size, perhaps 10 to 15 years old, already weighing several tons, but still manageable compared to adults. Or they might target old individuals past their prime, moving more slowly, perhaps suffering from injuries or disease, or sick animals, visibly weakened, struggling to keep up with the herd. This is what modern pack hunters do. Lions targeting elephants focus on calves, elderly individuals, or those clearly unwell. Wolves taking down bison or moose look for similar signs of weakness. The principle scales up. The strategy would likely be attrition, rather than a single, decisive blow. Mapusaurus teeth are blade-like, serrated, designed for slicing flesh, not for crushing bones like Tyrannosaurus, not for delivering one massive killing bite. These are tools for cutting, for opening wounds, for causing bleeding. This suggests a hit-and-run hunting style. Multiple attacks, each inflicting damage, each causing blood loss, gradually wearing down the prey until it can no longer resist. The pack spreads out, surrounding the target on multiple sides. One Mapusaurus rushes in from the left, jaws open, going for the upper leg or the tail base, muscle-rich areas where a bite can do serious damage. The teeth sink in, tear through flesh. Then the predator pulls back before the Argentinosaurus can retaliate effectively. Seconds later, another attack from a different angle, then another. The juvenile Argentinosaurus tries to turn, to face its attackers, but they're too fast, too coordinated. There's always another threat from a different direction. Each bite opens a wound. Blood flows, slowly at first, then more freely as multiple wounds accumulate. The Argentinosaurus begins to weaken. Its movements become slower, less coordinated. It starts to favor the injured leg. It's losing the ability to defend itself effectively. Anatomy guides the attacks. Argentinosaurus had massive body mass and a powerful tail that could sweep with devastating force. The head, mounted on that long neck, was relatively small and not a major threat. The teeth were for stripping vegetation, not defense. so Mapusaurus would focus on vulnerable areas while avoiding the most dangerous ones. The sides of the body, where muscle and blood vessels are closer to the surface. The upper legs, where bites could damage crucial tendons and muscles needed for movement. The base of the tail, rich with muscle and blood. Staying away from the business end of that tail would be critical. One solid hit could break bones, rupture organs, end a Mapusaurus's participation in the hunt permanently. And staying mobile, using agility as an advantage. A 4-ton theropod is far more maneuverable than a 20-ton or larger juvenile sauropod. Quick head and neck movements, rapid bites followed by immediate retreat, circling to attack from blind angles. All tactics that leverage superior agility against superior mass. Herd dynamics would play a crucial role. If Argentinosaurus moved in groups, and the predation pressure from Mapusaurus would strongly favor this, then the first challenge for predators would be separation. Picture the herd moving through a forested area along the river. The pack of Mapusaurus follows, hidden in vegetation, patient. They're waiting for an opportunity, a moment when the herd spreads out, when a juvenile lags behind, when terrain or circumstance creates separation. Perhaps the herd approaches a river crossing. The adults wade through first, testing the depth. Some juveniles hesitate at the bank. One lingers longer than the others, nervous, uncertain. The pack rushes from the forest, not attacking yet, but rushing, creating noise and movement, deliberately trying to panic the herd. The adults on the far side of the river vocalize alarm, start to turn back. But the current is strong, the footing uncertain. They can't respond quickly. The isolated juvenile turns to run, but the pack is between it and the rest of the herd. It's separated now, the crucial first step. Still dangerous, still capable of killing an unwary predator, but alone. Without the protection of adults, without the deterrent of group defense. Now the attacks begin in earnest. Terrain could be weaponized. The Winkle Formation was a braided river system. Channels, sandbars, muddy floodplains, steep banks. Complex terrain that created both opportunities and hazards. River margins would be particularly dangerous for something as heavy as Argentinosaurus. Mud that a Mapusaurus could run across might not support 20 tons of sauropod. A steep bank that the theropods could navigate might cause a juvenile titanosaur to slip, to stumble, to lose its footing. And in that moment of vulnerability, bogged in mud, struggling on a steep slope, awkwardly positioned in a narrow channel, the pack would strike. This is how modern predators often succeed, not through direct confrontation, but by using terrain to create disadvantage. Lions driving buffalo into rivers where they struggle. Wolves chasing elk into deep snow, where their long legs become a liability rather than an advantage. Scale it up to the Cretaceous, and the principle remains the same. The role differentiation within the pack adds another layer of sophistication. If Mapusaurus did hunt socially, the largest, most experienced adults would likely take the most dangerous roles. The direct attacks on the target, the deep bites that cause the most damage, but also require the closest approach. Subadults might focus on harassment, darting in from the flanks, creating distraction, cutting off escape routes without engaging in the most dangerous direct attacks. They're learning, gaining experience, participating at the periphery of the hunt, where the risks are somewhat lower. Juveniles, if present, might stay even farther back, watching, learning the patterns, the coordination, the timing that makes pack hunting work. This mirrors what we see in modern social predators. Lion prides show this kind of role differentiation. Wolf packs do as well. Younger, less experienced animals participate but take fewer risks, while they develop the skills and judgment needed for the most dangerous parts of hunting. Duration would matter. This wouldn't be a quick kill, not a single decisive moment where the prey falls and it's over. This would take time, perhaps hours, perhaps even longer. The pack makes an attack, bites are delivered, blood flows. Then the pack pulls back, giving the prey some space but not letting it escape, not letting it rejoin the herd. They rest, conserve energy, wait for the bleeding and shock to weaken the target further. Then another coordinated rush, more bites, more wounds, more blood loss. The Argentinosaurus grows weaker with each round. Its responses become slower. It can no longer run, only walk, then only stand. Its head lowers. Its breathing becomes labored. Finally, hours into the hunt, perhaps as the sun sets over the Cretaceous floodplain, it collapses. The legs give out. The massive body falls to the ground, crushing vegetation, sending up a cloud of dust and startled insects. The pack waits, cautious even now. Is it truly down? Will it try to rise? Only when they're certain do they approach to feed. But even with all these tactics, success would be far from guaranteed. Argentinosaurus was dangerous. Even a juvenile, even one that was sick or weakened, could kill a Mapusaurus with a lucky kick or a desperate swing of that tail. Adults nearby might respond to distress calls and come charging back, and no pack of Mapusaurus would stand against multiple adult Argentinosaurus in full defensive mode. The terrain might favor the prey instead of the predators. The targets might escape into water too deep for the theropods to follow, or into vegetation too dense for the pack to maintain visual contact and coordination. Weather could interfere. A sudden storm, flooding that changes the landscape mid-hunt, anything that disrupts the pack's tactics. So realistically, Mapusaurus probably hunted smaller prey most of the time. Other titanosaurs, less massive than Argentinosaurus. Large ornithopods, whatever was available and vulnerable. Attacks on Argentinosaurus would be special events. Rare, high-risk, high-reward hunts that the pack attempted only when conditions were ideal. The right target, the right terrain, sufficient hunger to justify the danger, and a group of experienced hunters working together. And there's one more possibility that's been suggested: flesh grazing. The idea that large theropods might inflict non-lethal bites on sauropods and return repeatedly to feed on the still living animal, treating the prey almost like a renewable resource. It's an intriguing idea that appears in some documentaries and popular accounts. But many paleontologists are skeptical. Multiple deep bites from predators the size of Mapusaurus would likely kill even a giant herbivore through shock, blood loss, and infection. The idea that Argentinosaurus could survive repeated feeding and heal between attacks seems implausible, given the scale of wounds that Mapusaurus teeth could inflict. More likely, if feeding occurred over time, it was because the initial attack had been lethal, but the prey took hours or even days to actually die, the pack feeding opportunistically as the animal weakened, rather than deliberately keeping it alive. So what's the most likely scenario? A combination of tactics adapted to circumstances. Pack hunting focused on vulnerable individuals, juveniles, sick, old, or injured animals. Use of terrain to create advantages. Hit-and-run attacks causing cumulative damage through blood loss. Coordination that allowed multiple predators to attack from different angles, overwhelming the prey's ability to defend itself. Patient, strategic hunting rather than reckless attacks. Assessment of risk versus reward. Willingness to abandon a hunt if it proved too dangerous or if circumstances turned against the pack. And most of the time, going after smaller prey. saving the attacks on Argentinosaurus for special circumstances when the potential payoff justified the considerable risk. This is how giants might have fallen in the late Cretaceous, not through simple, straightforward predation, but through complex, coordinated hunting strategies that pushed the boundaries of what's possible for terrestrial predators. Mapusaurus and Argentinosaurus, locked in evolutionary conflict, each pushing the other toward extremes of size and capability. And in the floodplains of Patagonia, 95 million years ago, when conditions aligned and opportunities arose, the drama of predation played out at the largest scale the land has ever seen. We'll never know exactly how it happened. The precise details are lost to time, but the fossils tell us it did happen, that these two giants coexisted, that their lives intersected, that in some moments, hunter and hunted came together in struggles that must have been among the most spectacular events in all of natural history. This is our best reconstruction, built from fragments and inference, from analogy and physics, from careful reasoning about what's plausible given everything we know. The hunt for the largest land animal by one of the largest predators, at the edge of what's possible in a world of giants. Now let us consider something more subtle. The possibility that Argentinosaurus did not exist in isolation, but as part of a web of relationships that extended beyond simple predator and prey. We have no direct fossil evidence for this. No snapshot of a small dinosaur perched on an Argentinosaurus's back. No preserved scene of cooperation frozen in stone. What we have instead is analogy, inference, and the patterns we see in modern ecosystems where large animals serve as living habitats for smaller organisms. These are speculations, yes, but they're informed speculations, grounded in what we know about how life works, how relationships form between organisms of vastly different sizes, how ecosystems create networks of mutual benefit. Let us explore these possibilities one by one, with appropriate humility about what we cannot know. First, consider the cleaners. In modern ecosystems, large animals often host smaller creatures that feed on parasites, dead skin, and other materials found on or around the giant's body. Oxpeckers on African mammals, cleaner fish on larger fish and marine mammals, cattle egrets following behind elephants and water buffalo. These relationships are mutualistic. Both parties benefit. The large animal gets relief from irritating parasites, reduced risk of infection from wounds where parasites have fed. The small animal gets a reliable food source and often protection from its own predators by staying close to something too large to be easily threatened. Could something similar have existed with Argentinosaurus? Picture early birds, small, probably not yet capable of sustained flight like modern birds, but mobile, quick, equipped with sharp eyes and beaks suited for picking. Or small theropods, the feathered relatives of birds, similarly sized to modern crows or ravens. These creatures could have picked ectoparasites from Argentinosaurus's skin. Ticks, perhaps, or Cretaceous equivalents. Insects that burrowed into skin folds or fed on blood. The Argentinosaurus, unable to reach much of its own body with its small head, would benefit from having these irritants removed. The birds or small theropods would gain an abundant, renewable food source. We know from other discoveries that tiny arthropods, such as beetles, had commensal or mutualistic relationships with feathered dinosaurs. Specimens have been found preserved together. It's not a stretch to imagine similar relationships with the largest dinosaurs, perhaps with cleaners specializing in the deep skin folds. The areas between scales, the places where parasites could hide and feed undisturbed without intervention. The dung would have been its own ecosystem. We discussed earlier, how Argentinosaurus produced enormous amounts of waste, hundreds of kilograms daily. That dung wasn't just fertilizer, it was habitat. Insects would have colonized it almost immediately. Dung beetles, or their Cretaceous equivalents, rolling portions away to bury as food for their larvae. Flies laying eggs that would hatch into larvae feeding on the nutrient-rich material. Other arthropods moving in to feed on the feeders, creating a multi-layered community centered on each pile. Small vertebrates might have joined them. Tiny mammals, mostly nocturnal in the Cretaceous, staying hidden during the day when dinosaurs dominated, emerging at dusk to pick through dung for insects and undigested seeds. Small lizards hunting the insects, perhaps even small dinosaurs, opportunistic omnivores that would eat almost anything, and Argentinosaurus would benefit indirectly. These dung-processing organisms broke down the waste quickly, returning nutrients to the soil. This enriched plant growth in the areas where Argentinosaurus regularly fed and defecated, creating a positive feedback loop. Better plant growth meant better feeding, which meant more dung, which meant more nutrients returned to the soil. It's a diffuse benefit, not a direct transaction like cleaner birds removing parasites, but it's real nonetheless, the kind of ecosystem-level mutualism that emerges from simple interactions repeated over time. Nesting sites would have attracted communities. If Argentinosaurus nested in communal grounds, and many titanosaurs appear to have done so, these sites would become temporary hotspots of resources. Eggs that failed to hatch, shells from successful hatches, tiny hatchlings that didn't survive. The vegetation trampled and disturbed by adults visiting the site, small animals would have been drawn to this abundance. Scavengers feeding on failed eggs or dead hatchlings, insectivores eating the flies and other arthropods attracted to decaying organic matter. Perhaps even some small dinosaurs or early mammals that specialized in finding and exploiting these seasonal resource pulses. And their presence might have provided small benefits to Argentinosaurus. By consuming food scraps and dead tissue, they reduced disease risk. By eating parasites and their eggs, they lowered pest loads for the hatchlings. The effect on any individual might be negligible, but across a nesting ground with dozens or hundreds of eggs, small improvements in hygiene could translate to measurably better survival rates. Mixed species herds are another intriguing possibility. In modern ecosystems, we sometimes see different herbivore species moving together. Zebras and wildebeest on the African savanna, for example. Each species has slightly different feeding preferences and different sensory strengths, and by moving together, they gain collective benefits. More eyes watching for predators, more ears listening for danger. Could smaller herbivorous dinosaurs have followed Argentinosaurus herds? The benefits for the small dinosaurs would be clear. Stay near the giants, and predators focus on the giants, or are deterred entirely by their presence. The sheer mass of an Argentinosaurus herd would provide protection that smaller animals could never achieve alone. And the cost to Argentinosaurus? Probably minimal. Small ornithopods feeding on low vegetation wouldn't compete with Argentinosaurus's high browsing. They might even be slightly beneficial, functioning as an early warning system, alarming at threats the giants hadn't yet noticed, giving the herd extra moments to prepare or move. It's speculative, but the ecological logic is sound, and we know that some modern large herbivores do tolerate or even benefit from the presence of smaller species in their vicinity. The concept of beta relationships is particularly fascinating. As Argentinosaurus moved through vegetation, that enormous body pushing through ferns and shrubs, that long neck sweeping through the canopy, it would disturb countless small animals. Insects taking flight, small vertebrates fleeing from the approaching giant, lizards and early mammals scrambling to escape being trampled. For insect-eating dinosaurs, this would create feeding opportunities. Rather than expending energy searching for prey hidden in vegetation, they could simply follow Argentinosaurus and catch the insects and small animals that were flushed out by its movement. We see this in modern ecosystems. Cattle egrets follow large mammals specifically to catch insects disturbed by their movement. Various birds follow army ant swarms for the same reason. The ants flush prey, and the birds catch it. Scale this up to the Cretaceous. Small theropods, early birds, perhaps certain types of pterosaurs, all learning that following Argentinosaurus meant easier hunting. They'd stay at a safe distance, close enough to benefit from the disturbance, far enough to avoid being accidentally crushed, and they'd feed on the bounty that the giant's passage created. For Argentinosaurus, the relationship would be essentially neutral, the small predators neither helping nor harming. But over evolutionary time, even neutral commensal relationships can shift toward mutualism if benefits emerge. The habitat modification that Argentinosaurus performed would have cascading effects. We discussed this earlier. Trampling paths, knocking down trees, opening canopies. This created microhabitats, small-scale environments with different conditions than the surrounding landscape. Some small dinosaurs and other organisms would have been specialists in these disturbed habitats. Species that thrived in the open clearings where sunlight reached the ground. Species that nested in trampled areas. Species that fed on the fast-growing pioneer plants that colonized broken ground. These specialists would, over time, become associated with Argentinosaurus, not directly dependent, but benefiting substantially from the landscape changes the giants created. And here's where it gets interesting. Some of these species might have provided reciprocal benefits. If certain small herbivores preferentially grazed on fast-growing plants that would otherwise compete with the slower-growing trees that Argentinosaurus preferred, then these small herbivores would indirectly maintain better feeding habitat for the giants. It's a diffuse mutualism, operating at the ecosystem level rather than through direct interaction. Argentinosaurus modifies the habitat. Small species thrive in the modified habitat. Some of those small species, through their own feeding, maintain conditions that favor Argentinosaurus's preferred food plants. Everyone benefits, though no individual organism is aware of the larger pattern. These are the kinds of relationships that might have existed. Subtle, indirect, often barely noticeable in the moment, but significant when viewed across populations and time. No fossil will ever prove them definitively. We won't find an Argentinosaurus with a small bird fossilized on its back, clearly in the act of removing a parasite. We won't find a snapshot of a mixed species herd moving together through the Cretaceous landscape. But absence of evidence isn't evidence of absence. And when we look at how modern ecosystems work, at the relationships that form between large and small organisms, at the ways life creates networks of mutual benefit, the pattern suggests that Argentinosaurus, like all large animals, probably existed within a web of such relationships. Picture it, an Argentinosaurus feeding in the morning sun. On its back, small birds or feathered theropods move carefully across the massive expanse of skin, picking at parasites, keeping the giant's hide clean and healthy. At its feet, dung beetles are already at work on the fresh waste deposited hours before. Nearby, a small ornithopod browses on low vegetation, gaining protection from the giant's presence while serving as an inadvertent sentinel, alerting at threats. As the Argentinosaurus moves forward, pushing through vegetation, small insectivorous dinosaurs follow at a distance, catching the insects that flee from the approaching giant. Behind, in the trampled path and disturbed soil, pioneer plants are already beginning to sprout, and later, small herbivores will graze them, preventing them from becoming the thick undergrowth that would make future passages more difficult. None of these relationships is dramatic. None involves obvious cooperation or communication. But together, they form a network, each species benefiting from the other's presence in small ways, each contributing something to the larger ecosystem function. This is how life works, at scales from the microscopic to the gigantic. Relationships form, benefits accrue. Over evolutionary time, these loose associations can become more specialized, more mutually dependent, or they remain casual, opportunistic, flexible, ready to form when conditions favor them, ready to dissolve when they don't. We'll never know for certain which relationships Argentinosaurus had, but based on everything we know about ecology, about how large animals interact with their environments, about how life creates connections and dependencies, it's almost certain that the giant was not alone, not isolated, but embedded in a community of relationships that extended far beyond the obvious dynamics of eating and being eaten. Even the largest animal that ever walked on land lived in relationship with the small, the subtle, the easily overlooked. Because that's how ecosystems work, not as collections of independent organisms, but as networks of interactions, each thread connecting to others, creating a tapestry of life where even giants depend, in ways large and small, on creatures they might never notice. This is the fuller picture of Argentinosaurus. Not just a solitary giant, but a hub in an ecosystem, a central node around which other lives organize themselves, a creature whose very existence created opportunities and niches for countless other organisms. Connected, embedded, part of something larger than itself, even at 70 tons, even as the largest land animal that would ever exist, still part of a community, still dependent on and depended upon by others. This is the ecological reality that fossils can only hint at, but that logic and analogy allow us to reconstruct with reasonable confidence. Argentinosaurus lived in relationship, and those relationships, though speculative in their details, were almost certainly real in their existence. Now let us consider something that might seem paradoxical. How was the largest land animal that ever lived similar to a sparrow? The question sounds absurd. What could a 70-ton giant possibly share with a creature you could hold in your hand? The scale difference is so extreme it seems to preclude meaningful comparison. And yet, Argentinosaurus was a dinosaur, and birds are dinosaurs, the only lineage that survived the end Cretaceous extinction, which means that modern birds and Argentinosaurus share a common ancestry, part of the same great evolutionary radiation that began in the Triassic period. More than that, they're both part of the bird line group of archosaurs. The fundamental body plan, the basic physiological systems, many of the behaviors, these were established millions of years before either birds or sauropods evolved, in the common ancestors they shared. So despite the incredible size difference, despite the 95 million years separating us from Argentinosaurus, despite everything that seems to make comparison impossible, there are genuine similarities, threads of connection running from the largest to the smallest, from the ancient to the modern, from the extinct to the living. Let us explore these connections one by one. First, the most basic, reproduction. Argentinosaurus laid eggs. Like all non-avian dinosaurs, like all modern birds, it reproduced by producing shelled eggs that developed outside the mother's body. This might seem trivial, of course dinosaurs laid eggs, but it's actually profound. The constraints of egg laying shaped everything about how these animals reproduced, how they grew, how they allocated resources to offspring. A mammal can grow its young internally, providing continuous nutrition and protection until birth. A bird or dinosaur must package all the initial resources into an egg, lay it, and then either incubate it or let environmental heat do the work. This creates fundamental limits. The egg can't be too large relative to the mother's body. It has to pass through the reproductive tract, which means even the largest animals produce relatively small eggs, and therefore very small hatchlings. We discussed this earlier. Argentinosaurus eggs about the size of ostrich eggs, producing hatchlings around 5 kilograms. The same basic constraint that limits bird egg size, reproductive anatomy, applied to the largest land animal that ever lived. And the nesting behavior itself shows parallels. Dinosaurs nested in colonies, huge nesting grounds with many shallow nests close together. We have evidence of this from other titanosaur species, and it's reasonable to infer similar behavior for Argentinosaurus. This is exactly what some modern birds do. Seabirds nesting in vast colonies on islands. Flamingos creating massive communal nesting areas. The principle is the same: safety in numbers, shared vigilance against predators, perhaps social facilitation, where the presence of other nesting individuals stimulates and synchronizes breeding behavior. An Argentinosaurus nesting ground would have been spectacular. Perhaps dozens or hundreds of these giants converging on the same general area, each digging a shallow nest, laying their clutch of eggs, and then departing. The eggs left to incubate in warm sand, perhaps with some vegetation piled on top to regulate temperature. No parental care once the eggs were laid, just like many modern ground nesting birds. The strategy is the same. Produce many offspring, accept high mortality, count on a few survivors rather than investing heavily in protecting and raising each individual. The growth patterns show striking similarities. Bone studies of sauropods reveal rapid juvenile growth, young animals reaching large size quickly compared to most reptiles. This is bird-like growth, not reptile-like. Modern crocodiles and lizards grow slowly, continuously, over many years. Birds grow rapidly, reaching adult or near adult size within months or a few years, then slowing dramatically. Argentinosaurus appears to have followed the bird pattern. Fast early growth to large size, supported by a high metabolic rate and efficient resource processing. This allowed it to move through the most vulnerable juvenile stages quickly, reaching sizes where predation became less of a threat. It's the same strategy that allows a baby swan to grow from a tiny cygnet to an adult-sized bird in one summer. The scale is different, weeks versus decades, but the pattern is the same. Grow fast, reach safety, then slow down. And that brings us to metabolism. Sauropods likely had relatively high metabolic rates and efficient respiratory systems, closer to birds than to living reptiles. Not exactly bird-like, they were too large for that, and size itself imposes constraints, but much more active than the sluggish, cold-blooded dinosaurs of old misconceptions. The evidence comes partly from those growth rates we just discussed. You can't sustain rapid growth on a low metabolic rate, and it comes from the bone structure, which shows signs of continuous, active remodeling. The kind of dynamic bone tissue associated with warm-blooded animals, and crucially, it comes from the respiratory system. The air sac system is perhaps the most bird-like feature of sauropods. Sauropods, including titanosaurs like Argentinosaurus, had extensive pneumatic chambers in their vertebrae, hollow spaces filled with air. These weren't just for weight reduction, though that was certainly beneficial. They were part of a bird-like system of air sacs and flow-through lungs. Modern birds have the most efficient respiratory system of any vertebrate. Air flows in one direction through the lungs, with air sacs acting as bellows and reservoirs. Oxygen extraction is continuous during both inhalation and exhalation. It's far more efficient than the mammalian system of tidal breathing, in and out through the same passages. Argentinosaurus almost certainly had a similar system. The pneumatic spaces in its vertebrae are exactly what we'd expect to see if air sacs extended from the lungs into the skeleton, just as they do in modern birds. This would have served multiple functions: better oxygen uptake, supporting that higher metabolic rate; heat dissipation, air flowing through the body helps cool it, particularly important for an animal so large that overheating would be a constant risk. And yes, weight reduction, making those enormous vertebrae lighter than they would otherwise be, reducing the energetic cost of supporting and moving that long neck. The skeletal lightening itself is a shared adaptation. Birds have hollow bones to reduce weight for flight. Argentinosaurus had hollow bones to reduce weight for being enormous on land. Different selective pressures, similar solutions, both arising from the common architectural heritage of the dinosaur lineage. These air spaces made bones lighter for their size without sacrificing strength. It's elegant engineering, removing mass from the interior where it contributes least to load-bearing capacity, while maintaining or even reinforcing the outer walls where stresses are highest. A solid-boned animal of Argentinosaurus's size might have been impossible, too heavy to move efficiently, too demanding of skeletal strength beyond what bone tissue can provide. The air-filled bones helped make gigantism viable. Behavior shows parallels too. Herding in sauropods mirrors flocking in birds, coordinated movement, collective defense, shared use of feeding or nesting areas. The specific mechanisms might differ. Visual coordination in one, perhaps both visual and vocal in the other, but the function is the same. There's safety in numbers, many eyes watching for predators, collective knowledge of where resources are, social bonds that might provide support during difficult times. A herd of Argentinosaurus moving across the Cretaceous landscape and a flock of geese migrating across a modern sky are engaged in fundamentally similar behaviors, separated by scale and medium, but united by the advantages of group living. Communication would have been important. We don't know what Argentinosaurus sounded like. The soft tissues of the vocal apparatus don't fossilize, but social, herd-living animals almost always communicate extensively. Modern birds use both visual displays and vocalizations. Postures communicate aggression, submission, alarm. Calls maintain flock cohesion, warn of danger, attract mates. Argentinosaurus probably used similar strategies. That long neck could be raised in threat or lowered in submission. The body could be turned toward or away from another individual, communicating intent, and quite possibly vocalizations, perhaps low-frequency calls that carried across long distances, allowing widely dispersed herd members to stay in contact. Birds descended from dinosaurs use these communication methods. It's parsimonious to assume that dinosaurs, including sauropods, used them too. Sensory capabilities likely paralleled those of large ground-dwelling birds. As diurnal, large-bodied herbivores in open landscapes, sauropods probably relied heavily on vision. good visual acuity to spot predators at a distance, to navigate terrain, to recognize herd mates, to assess vegetation quality, active lifestyles during the day, perhaps with periods of rest during the hottest midday hours, sustained, active foraging, moving slowly but continuously, feeding almost constantly to meet those enormous energy requirements. Large birds like ostriches or emus show similar patterns: diurnal activity, good vision, sustained movement through open habitats, constant vigilance for predators, social cohesion through visual contact. Scale it up 40 or 50-fold, and you have a plausible picture of Argentinosaurus' daily life. These similarities exist despite, or perhaps because of, the vast difference in scale. The fundamental body plan works across an enormous range of sizes. The same basic respiratory system functions in a hummingbird and would have functioned in Argentinosaurus. The same reproductive strategy, eggs, colonial nesting, high offspring mortality, works for penguins and would have worked for titanosaurs. This is the power of a successful evolutionary design. Flexibility, scalability, adaptability. The bird-line archosaurs evolved a suite of traits in their common ancestors: egg-laying, efficient respiration, pneumatic bones, active metabolism, social behavior. These traits then allowed different lineages to explore different sizes, different lifestyles, different ecological niches. Some got smaller, eventually evolving flight, giving rise to modern birds. Others got larger, much larger, becoming the sauropods that would dominate terrestrial herbivore niches for over 100 million years. So when we look at a modern bird, any bird, from a tiny warbler to a large ostrich, we're seeing a distant cousin of Argentinosaurus. They share that common ancestry. They share fundamental traits inherited from those common ancestors. And in some cases, they've independently evolved similar solutions to different problems because the basic archosaur body plan predisposes them towards certain solutions. This doesn't mean Argentinosaurus was bird-like in any simple sense. It was its own thing, magnificently adapted to being the largest land herbivore. But the threads of connection are real. The largest and the smallest, the ancient and the modern, the extinct and the living, all part of the same evolutionary story. When a goose migrates in formation with its flock, using vocalizations to maintain cohesion, it's engaging in behaviors that might have parallels in how Argentinosaurus herds coordinated their movements. When a bird's respiratory system pulls oxygen efficiently from the air, that system is fundamentally similar to what kept Argentinosaurus alive and active. When a bird lays eggs in a colonial nesting area, it's following a reproductive strategy that served titanosaurs for tens of millions of years. The connections run deep, deeper than the obvious differences in size and time and circumstance. This is one of the beautiful insights that paleontology and evolutionary biology provide. The ability to see relationships across vast gulfs of time and scale, to recognize that life on Earth is unified by common ancestry, that the same solutions arise again and again, because they're built into the basic template. Argentinosaurus and a sparrow are related. Not closely, they're separated by the entire breadth of the dinosaur family tree and 95 million years of evolution, but related nonetheless, inheritors of the same fundamental body plan, users of the same basic physiological systems, practitioners of similar behaviors adapted to different scales. This perspective transforms how we see both. The sparrow becomes more remarkable, a tiny descendant of mighty giants, carrying forward the legacy of the largest land animals that ever lived. An Argentinosaurus becomes more familiar, not an alien creature from an incomprehensible past, but a relative however distant, of animals we see every day. Both dinosaurs, both archosaurs, both part of the same grand experiment in what a vertebrate body can become. From 5 grams to 70,000 kilograms, from flitting through gardens to shaking the earth with each step, all variations on a theme, all expressions of the same fundamental design. This is the deepest connection between Argentinosaurus and modern birds. Not just that they're related, but that they demonstrate the remarkable flexibility and power of evolutionary processes to take a single body plan and express it across an almost unimaginable range of forms. The largest land animal that ever lived shares fundamental similarities with the smallest birds flying today. And that fact, unlikely as it seems, counterintuitive as it appears, is simply true. A testament to the unity of life, to the power of common ancestry, to the way evolution takes what works and scales it, modifies it, adapts it to new circumstances while retaining the core features that made it successful in the first place. This is Argentinosaurus, understood not in isolation but in relationship to its environment, to its contemporaries, and yes, to the distant descendants of its cousins that still fly through our skies today, connected across deep time by threads of biology that even extinction cannot sever.